Hey, welcome back to Math with Patrick. Today is January 9th, and we are solving the ninth problem from this Daily Epsilon calendar. And today I am once again joined by my math magician, Mr. Quill, over here. And he'll be helping us solve this problem today. Okay, so find the number of factors of 36. Compared to the last 2 days, this is honestly a nice change of pace. Um, like all the other problems, the answer is hiding in the corner. It's just a 9, today's date, and it's up to us to figure out why this 9 is correct. So going over some vocab words, looks like there's one important one right here. A factor is just defined as a number that's being multiplied, and I want to find some numbers that multiply together that get the number 36. And although I can use the word factor to refer to a negative number, like here I can say that if I do negative 2 times 4 equals negative 8, I can say that this negative 2 is a factor because it's a thing being multiplied. For this search of factors of 36, I'm just going to consider whole positive numbers instead of thinking about possibilities of negatives here. So the first positive number to check is 1. And to check if a number is a factor of another, I need to do 1 times another whole number equals my target number, 36. And this right here, where I have multiplication and I don't know one of my numbers, this actually feels like a division problem to me, where I could rethink it as 36 divided by 1 equals what? And this is a fairly obvious question and a fairly obvious answer. A 36 should go into this spot, and I have found actually 2 factors of the number 36, 1 and itself. So here are our first 2 factors, 1 and 36. And the next whole positive number to check is 2. Can I do 2 times something is 36? And I'll answer this with division. Maybe I'll use long division on this one. I'll ask myself how many times does 2 go into 3? It goes in once. I'll do that multiply and then the subtract step. I'll bring down the 6. And then I'll ask how many times does 2 go into 16? That's 8 times. And then just to kind of complete it, I'll do that 8 times 2. Gets me a 16. My remainder is 0. So this demonstrates that 2 is a factor. And also by doing the division, I found that 18 is a factor as well. The next number to check is 3, because that's the next whole positive number. And same thing, times something is 36, so I should think about this as a division problem. And I'll think about it differently than the last one. If I'm thinking 36 divided by 3, that says split 36 into 3 groups. And I can tell that if I do 12 plus 12 plus 12, I get 36. That's because all the 10s add up to a 30, and all the 2's add up to a 6. So that demonstrates that 3 times 12 is 36, and there is yet another factor pair. And the next number is 4, so I'll check 4. 4 times something is 36, and I'll do this one differently than the other two. I know that 4 times 10 is 40, and that's just because counting by tens is fairly easy. And so if I take out one of those 4's, then I should reduce this number by 1 to reduce this number here by 4. I'm like taking one of the 4's out from my count. So 1 less than 10 is a 9, so I know that 4 times 9 is 36. I guess I should try 5. So 5 would be the next number. 5 times something is 36. But I know something about multiples of 5, where they always end in a 5 or a 0. So as I'm counting up, all of these numbers end in a 5 or a 0. So once I get around 36, I'm not going to hit it. So it won't go in evenly. Or in other words, this number right here won't be a whole number. And so for the case of this problem, I'm not going to consider it as a factor. So 5 won't work. I'll do 6 though. It's the next number anyways. And why not? Let's count up by our 6's. 6, 12, 18, 24, 30, and there it is, 36. So I can count up 6 times, or in other words, 6 times 6 gives me 36. And looking at the factors, on the left side, they were increasing, and on the right side, they were decreasing as we look down the list. And they lined up at this 6 down here. So I know that I don't need to keep going, because if I keep searching for factors, I'll just go back the other way on this list. I've already found all of them. And I don't want to double count that 6. So we can go 1, 2, 3, 4, 5, 6, 7, 8, 9 factors. And that is the answer to this problem. We have found all 9 factors of the number 36. We're all done. You're still here? Well, we solved the problem. You want more math? Okay. Well, there's one more thing I guess I could share. So you know how in this problem we stopped at this 6? That's just kind of because it showed up twice. I knew that I didn't have to keep finding the factors. I found them all. I found, the biggest one on this side of the list, and I knew that any bigger, I would just be repeating myself. This idea of finding this biggest factor is actually quite useful when the number you're trying to find factors of doesn't factor that easily. For example, a prime. So if you're trying to find factors of a number and it's just not working, maybe the number is prime, but it would be nice to know when to stop. And the stopping point we can kind of see in this problem right here. If I take the square root of this number, 36, for this example, I get 6. And that 6 is a convenient stopping point, because if I went any past it, I would just be circling back on other factors that I've kind of already tried. So let's take this idea and see if we can find any factors of 113. Of course, we can always start with 1 times 113. That's always going to work for every number. 1 times itself is still the number. But then let's keep trying other numbers. So I know 2 is not going to work. 113 is not even, or it's odd. So 2 is going to not divide unevenly. If I try 3, there is a trick with 3s, where if you sum the digits of a number and the sum is also divisible by 3, then the original number is 2. So if we take 1, 1, and 3 and add them up, we get a 5. It's not divisible by 3, though, so I know that 113 isn't. Just to kind of show the rest of this example, if I chose like 114 instead, those digits add up to 6. So I do know that 114 is divisible by 3, but I would have to do a little bit more work to figure out what 114 divided by 3 actually is. But regardless, this trick tells me that 113 is not divisible by 3, so there's no need to actually do any division here. The next number to check could be 4, but I kind of already accounted for that by checking the 2 earlier. Knowing that it's not divisible by 2 means that, well, I can't divide it by 2. And trying to divide it by 4 is like dividing it by 2 twice. So I know that neither of these are going to work. So by already knowing that 2 is not a factor, I know that 4 isn't either. The next number that we should check is 5. And I'll do that idea from earlier, where if it ends in a 0 or a 5, it's divisible by 5. Ends in a 3, so not really. So 5 doesn't work. After 5, we have 6, though knowing that 2 isn't a factor and 3 isn't a factor, that's enough to tell me that 6 won't work either. And ultimately, what we're doing here is we're just checking the primes. We don't need to check any composite numbers or ones that we can break up into other factors, because once we break it up, we've already tested that, say, for this example, 2 doesn't work. So if 2 doesn't work, then 8's not a factor either. So there's really no good reason to check any other numbers besides primes until I find my first one. So after 5 and 7, the next prime is 11. And here's where this idea of knowing when to stop comes into play. I know that 11 times 11 is 121, and that is already bigger than 113. And so if I took, like, say, the square root of 113, I know that I get something that is less than this 11 right here. And that square root tells me when to stop. And if the square root of 113 is less than 11, I actually don't even need to check this one. It would be too big because, 11 times 11 is 121. So it's never going to work for 113. 113 is just too small. So this 7 is actually the last prime I need to check. And if this 7 is not a factor, then I will claim that 113 is prime. I have checked all my factors, I've checked all the primes. 11 is too big by that square root idea. So let me do a little bit of division. I'll do 113 divided by 7, and we'll see if 7 is a factor of this number. 7 goes into 11 once. Here's that multiply step. Here's the subtract step. And 7 goes into 43 6 times, because 7 times 6 is 42. But I get this remainder of 1. And this tells me that it doesn't go in evenly. Or, in other words, 7 isn't a factor. And none of these numbers worked. So none of the primes were factors, and then 11 was too big because of that square root idea. And I can stop here at the 7. I don't need to go any further. Don't need to search for more numbers. I know that 113 is now prime. That's kind of cool. I didn't even have to check that many numbers. I mean, I checked like 6, but it's cool to know that I don't need to check like 17, another prime number, but 17 would be too big anyways. So I just wanted to show you the idea where if you take the square root of the number you're trying to find factors of, that kind of tells you where to stop. And maybe that can help you in your search for when you're factoring these larger numbers, especially when they're primes. Okay, now we're all done. Thanks for hanging out for this day, this problem, and I'll see you tomorrow. Bye.